In this video, we'll go over the homework that follows the lecture 14.3 that is dedicated to the Simpsons approximation. And as always, I hope that you watched the lectures, and let's go ahead and jump right into the homework. And the first problem is asking us to use the Simpsons rule with two subintervals to estimate some integral. So I got this image here, and let's set up the problem. So a is 0. This is my a, or x0, and b is 2. So this is my b. And we have two subintervals, so here's the partition. And the idea is that we are using parabolas instead of rectangles or trapezoids. So it is less intuitive, and we have to rely more on the formula, which kind of outlines the pattern rather than requires us to memorize it. But here's the formula. So in this case, S2 will be equal to delta x, which we still need to find. A is 0, B is 2, delta x will be, well, I also forgot n. N is 2, so delta x will be b minus a over n. In this case, it will be just 1. And the formula for Simpson's approximation is delta x over 3. And inside of the parentheses, we have f of x 0. And then here, there goes the rotation 4, 2, 4, 2 until we reach the last one. And here we start with 4 of x1. And we don't even get to rotate between 4 and 2 because we already reached the end of the partition. Now we're going to use the graph to evaluate the function, and at each of those points, so f of x0 is 5, f of x1 is 7, and f of x2 is 4. So we get 1/3. 9 plus 28 is 37. So 37 thirds, that's just 12.33, etc. So if we have to round, we'll round it like this. Now it's asking us to enter the exact answer. So the exact answer is 37 over 3. Did I enter it? Yes. All right. Let's go to the next problem. A is 2, B is 6, N is 2. So delta x is equal to b minus a over n. So it's 2. Now we need to create the partition. Again, I don't need to draw the whole function, but I do need to figure out the partition. So we're going to start at 2 and go all the way to 6 in increments of 2. So here it's going to be really fast. 2, 4, 6. So this is my partition. And once again, we're using two subintervals. So my S2 will be equal to delta x over 3 times f of x0 plus 4 f of x1 plus f of x2. Delta x is 2, f of x 0. So in this case, actually, I don't know wrote, did I do it the same way before? Yeah, I guess I did. Here instead of x0 we can just write 2. Here instead of x1 we can just write 4, just to make it very clear what's going on. And here instead of x2 we can write 6. So f of 2 according to the table is 15, f of 4 is 57, and f of 6 is 131. And I'm just going to type this up in Desmos. So we have 2/3 times 15 plus 4 times 57 plus 131. And we can express it as a fraction, 748/3 is the exact answer. In this problem, a is equal to -3, b is equal to 1, n is 4, so delta x is b minus a over n, and oh, that was quick. So we actually looking for the error bound, which I didn't realize. So to find the error bound, we need to recall the formula, and the formula is covered in this lecture, and it's about somewhere. I think it's right over here. I think it's an example. Oh yeah, there it is. So the formula is k b minus a to the power 5 over 180 n to the power 4. And in our case, we know everything, and we don't need delta x here. But we do need k. And what is k? K is the upper bound for the fourth derivative. So we need to find the fourth derivative in order to find its upper bound. We have e to the power 2x. The first derivative is 2 times e to the power 2x. The second derivative is 4 times e to the power 2x. The third derivative is 8 times e to the power 2x. And the fourth derivative is 16 e to the power 2x. And what's worth noticing here is that the fourth derivative is an exponential function, increasing, so it achieves its minimum on the left at -3 and achieves its maximum on the right at 1. So it totally makes sense to set k to be equal to the fourth derivative evaluated at 1, which is 16e squared. And now we have all the ingredients. And I'm just going to delegate this computational task to Desmos. And the answer is 42.0355, and we're gonna round up to the nearest hundredth. So the answer is 42.04. Let's double check the formula. So the power here is 4. So it's gonna be 16 times smaller. A is -3, B is 1, N is 4, K is unknown. So to find K, we're going to find the fourth derivative. Here you can notice pretty quick that the fourth derivative is the same as the function itself. And once again, we're lucky that this is a monotone, strictly increasing function, so it reaches its minimum at -3 and reaches its maximum at 1. So it makes sense to set K to be equal to the output of the fourth derivative at 1. So it's just 2e, and now we're plugging in all the ingredients into the formula. And let Desmos do all the work. And let's do another problem. Now we have to estimate an integral. Using Simpson's rule with 4 subintervals. A is 2, B is 6, N is 4, so delta x will be b minus a over n, so it's going to be 1. So our partition will be from 2 to 6 in increments of 1, so 3, 4, 5, 6. This is my x0, x1, x2, x3, x4, and the formula for S4 is delta x over 3 times f of x0 plus 4 f of x1. Now we're going to rotate between 4 and 2 until we get to the end, and here the end is near, so we don't get to rotate it too much, but this is the pattern for the Simpson's approximation. So here we have delta x is 1, x0 is 2, x1 is 3, x2 is 4, x3 is 5, and x4 is 6. So here we can evaluate this quadratic function by hand. However, I'll use Desmos. So I'm going to define this function. And I'm going to produce the table of inputs outputs here. And we can do it by hand. Which could be very tedious and long, or we can just, again, use the power of Desmos and just type f of 2 plus 4 f of 3 plus 2 f of 4 plus 4 f of 5 plus f of 6, and that seems to be a little faster. So the answer is 192. Let's do another problem. A is 1, B is 5, N is 2, delta x is B minus A over N, which is 2. So the partition will be going from 1 to 5 in increments of 2. So this is my x0, x1, and x2. And S2 will be equal to delta x over 3 f of x0 plus 4 f of x1 plus f of x2. So f of x1 is just f of 1 plus 4 f of 3 plus f of 5 f of 1, and here I need some help with Desmos. So either we can do it by hand, or we can use technology. Such as Desmos, to make the computations a little easier. right, so another question on finding the upper bound. And we have A is -1, B is 1, N is 2, and we need to find K. To find K, we need to find the fourth derivative. Here, we can observe that the fourth derivative is exactly the same as the first derivative, and since the function is monotone, it means it obtains its minimum at -1 and its maximum at 1. So we can set K to be equal to the value of the fourth derivative evaluated at 1, which is just 2e. And now we're ready to find the upper bound for the error. It's going to be, what was the formula? It's going to be K times B minus A to the power of 5 divided by 180 N to the power of 4. So this is the formula. And let's go plug it in. And we are asked to round up to the nearest hundredth. So the answer is going to be 0.07. Same problem. A is -1, B is 1, N is 4. We don't know K, but f of x is equal to e to the power 2x. F prime of x is equal to 2e to the 2x. The second derivative is 4e to the power 2x. This is third derivative. And finally, this is fourth derivative, which is exponential function. Therefore, it's monotone. Therefore, it obtains its minimum at -1. It obtains its maximum at 1. So it does make sense to set k equal to the fourth derivative at 1, which is 16e squared. So now we can find the upper bound for this error. It's going to be 16e squared 1 minus -1 to the power of 5 divided by 180 n to the power 4. And let's go ahead and compute this expression. So the answer is 0.0821, which is approximately 0.09 if I had to round up to the nearest hundredth. And it looks like we completed the homework. If you have any questions about application of the Simpson's rule, please let me know.